Hassler here. I'm going to do the in-class lesson for 3.8. Today in groups at the boards, students were presented with this always, sometimes, or never. So it says below is a set of 8 statements. Decide if each statement is true for all values of x. That would be infinite solutions, or we've talked about this as being all real numbers. So I'm actually going to cross that out and say all real numbers. For some values of x, or for no values of x, meaning no solutions. If the answer is some, describe which values or show them on a number line. And so we worked through 1 and 2, paused and talked, 3 and 4, paused and talked, 5, 6, 7, 8. So I'm going to work through these so you can see what the outcomes were. This first one says 3x is less than 3x plus 5. And I'm thinking to myself, well, if I pick any number, let's say 1, and I substitute that in for x, then yeah, adding 5 on this side is always going to make it bigger than not having anything added onto this side, right? In essence, I would end up with 3 is less than x. And so it turns out that this is always true. If I substitute a number in for x and add 5 on only one side, then this result will always be bigger than this result, or this result will always be smaller. Another way to consider that is if I were to solve this inequality, I could subtract 3x on both sides. If I did that, I have 0 on this side, less than, the x's go away here as well, 5. And this is actually a true statement. And so this inequality is true for all real numbers, or all values of x. Let's take a look at problem 2. In problem 2, I do not have variables on both sides. And so because I don't have variables on both sides, I'm not substituting a number in on both sides. It might actually matter what number I substitute in. And so I'm just going to go ahead and solve this. Remember, I can multiply both sides by 2. 2 times a half is 1, and so I have 1x less than 8. And so this is only true for some values of x. I'm going to go ahead and put this on the number line. Right, I can pick a couple of values lower than and larger than 8. For all values of x less than 8, so that means that 7 works and 6 works, and in between 7 and 6 works, and anything over on this side of that number line works. 8 does not work because there's no equal to bar, but any number to the left of 8 does make this true. I could substitute in, for example, 6. For x, half of 6 is 3, and so yeah, 3 is less than 4. So it's only true for some solutions, and the solutions that it's true for are any numbers that are less than 8. And so this is really what we worked through today. It turns out that when there's a variable just on one side, it's going to be some solutions. If I divide by 5, it's going to be true for all numbers that are greater than or equal to 4. There's only one x on one side. It's not on both sides. So again, it's only going to be true for some. If I divide by 4, the numbers that work are all numbers that are bigger than or equal to -6. When I take a look at numbers like 5, 6, 7, and 8, 5 looks a little different because I notice on 5 that there is an x on both sides of this inequality symbol. And so I think to myself, okay, well, I'm going to do what I did in problem 1, right? Like, what if I test the number 1? If I substitute 1 in, I get 8 is bigger than 1. And so, yeah, that works. That's great. But just for fun, what happens if I substitute -1 in, right? So 8 times -1, is that bigger than -1? Well, now I get -8 is bigger than -1, and well, that's not true. That doesn't work. And so if I go back up here to problem 1, I notice that the x terms on each side of the inequality were the same x terms. Both were 3x. Versus in problem 5, my x terms are actually two different x terms. And so that's going to matter in my end result. So I'm going to go ahead, I'm going to subtract x on both sides. When I do that, I get 7x is greater than 0. There's nothing left there. And to isolate this x, I can divide by 7. And when I do that, I get x is greater than 0. It turns out that all numbers that are, that should be a 1, all numbers that are bigger than 0, so not including 0, if I put 0 in here, I would get 0 is greater than 0, and that's not true. But all numbers bigger than 0 make this work. That's why an x value of 1 worked, and an x value of 1 did not work. Okay, so we have to be careful. Just because there's variables on both sides doesn't mean I end up with this all real numbers. I still have to go through and check it. Again, on problem 6, I only have a variable on one side, so it's not possible to end up like problem number 1. I'm going to divide both sides by -4. And remember that when I divide by -4, I have to flip that inequality symbol to maintain the truth. And so this is only true for sum, any number that is less than or equal to -6. Again, I have a variable just on one side, and so it's likely that my answer is going to be a sum. If I subtract 7 from both sides, I get 2x is greater than or equal to 16. And if I divide by 2 on both sides, I get x is greater than or equal to 8. And so this is true for only some of my answers. Any number that's 8 or bigger would make this inequality true. If I take a look at problem 8, again, I have these variables on both sides, and so I guess it could be like problem 5, or it could be like problem 1. In problem 1, again, we said the variable was the same on both sides. That one turned out to be all real numbers. Any number for x would work. On problem 8, the variables were different, at different coefficients, and so it turned out the answer was sum, only for some values of x. And so we have to do a little bit more work here to verify, right? So I'm going to subtract 2x on both sides. When I do that, my x terms go away. I have -7 is greater than, and these x terms go away. So -7 is greater than 6. That is not true. I have no more x's to isolate, and I have a false statement. And so there are no values of x, or no solution. There are no values of x that are going to make this statement true. And so things that I notice are that when again, coming back up here to problem 1, when my variables are the same coefficient on each side of the inequality, and I go to get rid of those variable terms, I'm left with a true statement, then every number would make that true. If my variable terms are the same on each side of the inequality, and I get rid of those variable terms completely, and I have a false statement, then there's never going to be a value of x to make that statement true. Okay, and so that's what we talked about in class today. This last one says, Jorge says that solving inequalities is easy. All you have to do is replace the inequality with an equal sign, solve for x, and then put the inequality symbol back in. Will his method always work? If so, or explain why, or give a counterexample, and a counterexample would be an example that doesn't work. So it looks to me like he's going through and he's going to subtract 15. So you get 6, that works out. And then it looks, I'm putting a check mark here. And then it looks like he's dividing 3. 6 divided by 3 is 2. And then he puts that same inequality symbol back in. And I could check it, right? I can check to see if the original inequality works for any number less than 2. 0 is less than 2, so I'll try it for 0. And if I substitute 0 in, I get 15 is less than 21, and that's true. So it seems reasonable what Jorge is saying. However, what if you have to divide or multiply by a negative? Remember, we have to flip the sign. And so if this originally said -3x plus 15 is less than 21, and I go through the same process of solving, right? I subtract the 15. So if I do the equal sign like they did, subtract the 15, I get 6. Divide by -3, first of all, I get -2. But in this process, I would have to take the original inequality symbol and I would have to flip that. If I use Jorge's method and just put that inequality symbol, the original one, back in, I would be wrong. In this particular case, when I flip that symbol, I can pick any number bigger than -2 and substitute it in. -1 is bigger than -2. If I do that, I get +3 plus 15. That's 18. Yep, that's less than 21. So in order to maintain the true statement of the original, I had to flip my inequality symbol at the end so that I can maintain that truth. Jorge's method doesn't work in this case. And so that would be my counterexample, is if I have to multiply or divide by a negative, then Jorge's example doesn't work. And so then as a class, we talked about this idea of some, all, or none. I filled out this little quick notes section with them, and then they worked through the check your understanding with their team. So let me fill this out for you here. We had said that sometimes you can get all real numbers, like all values of x work. And so an example of that would be if I have like 3x plus 5 is less than or equal to 3x plus 10, right? And we said that my variable on each side is exactly the same. If I get rid of that variable, in this case, I'm subtracting 3x to do that. I have 5 is less than or equal to 10. That's always true. And so there's no x left to isolate. I have this true statement. And so my answer would be all real numbers. You guys had talked in the past about that being infinite solutions. Another example would be if I have no solution. There's no number for x that would make this true. So an example of that would be if I have like 3x plus 5 is greater than or equal to 3x plus 10. Again, notice that my variable term is the same on both sides. So if I subtract 3x to get rid of it, I would have 5 is greater than or equal to 10, and well, that's false. That's not true. And so in that case, there is no value of x that would ever make that inequality true. And the other option is if I had something like some solutions. When we talked about equations, we either had infinite solutions or all real numbers, no solution or one solution, when you're just equal to that number. With inequalities, we could have some solutions, right? And equal to like half of the number line. And so an example of that would be something like 3x plus 5 greater than or equal to negative 3x plus 10. And so in this particular case, notice I have variables on both sides, but they're not exactly the same. They're different. And so if I, added 3x to both sides, my x terms don't cancel on this side. I actually add up to get 6x plus 5. They cancel here, okay? And then I would subtract my 5. 10 minus 5 is 5. And then I would divide by my 6. So I get x is greater than or equal to 5, 6. And so I have some solutions. My solutions are all numbers that are bigger than 5, 6 or equal to 5, 6. So these are the possibilities. The fact that we're adding variables to both sides mean that I have these options as my answer, not just this last option like we've been working with. And the final statement that I want to make is how we would graph these. And so for all real numbers, means every single number on the number line gets graphed. So you can put any 3 numbers on that number line. I always like to just do -1, 0, and 1. And there's no open or closed circle. Every single number gets graphed, so you're literally graphing that entire number line. Every number works to make that inequality true. Versus something like no solution. Again, I want to put some numbers on that number line, so -1, 0, and 1. But there's not a single number that works for this. There's no number to make this statement true, so there's literally no graph. It's just that instead of leaving it blank, which means it looks like I forgot to graph it, I at least want to indicate that there are numbers on my number line. I didn't forget to graph. It's just that there's no graph. Or you could write no graph. Versus this is what we've been talking about in class, right? I've got 5/6. I've got, 0. I've got 1 somewhere here on my number line. And greater than or equal to means I have this closed circle at 5/6. And any number that's bigger than 5/6 would work. So only like half my number line is going to work as a solution. Okay, so the students then worked on the check your understanding. The answer key is posted for you, and the homework was the 3.8 practice. If you have questions, let me know.